Let's start with question number 1. A circular portion of radius r centered at a distance of a from the center of a circular disk of radius r0 is cut out. The mass of the disk per unit area is m. Find the moment of inertia of the disk about an axis passing through the center of disk of radius r0. A figure is given to us, and we're asked to find the moment of inertia of the disk about the axis passing through the center of the bigger disk with radius r0. So let's see how we go about this question.
Now, as we know that moment of inertia for a body is sigma mi ri square. Here you see that mi is also a scalar quantity, ri is also a scalar quantity, since it's basically only the distance of the particle from the axis.
Right.
So here we see that moment of inertia is basically a scalar quantity,
Right.
which can basically be very easily added, subtracted, or can be done anything. So here what we'll do is we'll use a very smart idea. We'll assume that the part of the disk is not removed, and we'll find the moment of inertia of the entire disk about the required axis.
Okay.
And we'll also find the moment of inertia of only the removed part about the axis which is required, and we'll subtract it from the entire
because
quantity.
it's mass, right?
Yeah.
So we can easily add and subtract masses.
Right.
Yeah.
It's
Removing
very analogous to
a mass is as good as subtracting the mass.
Right.
Right.
So it's very analogous to the mass concept. Similarly, we'll do for moment of inertia. So here, first we'll try to find the moment of inertia of the entire bigger disk with the assumption that the central part is not removed. So for that, first we'll need to find the mass of the entire bigger disk, which will be given by m1. Let's assume that m1 is the mass of the entire bigger disk. So this will be equal to m, which is the mass per unit area, into pi r0 square. This will be the area of the bigger disk basically. So here we have found out the mass for the bigger disk. So the moment of inertia I1 will be equal to m r square by 2. Here m will be m1 and r will be r0, since we are considering the bigger disk.
Right.
So
this comes from the standard result.
Right.
Right. Okay.
So here we'll put in the values to find out that the moment of inertia for the entire bigger disk, with the assumption that the smaller part is not removed, is m into pi r0 square into r0 square by 2, which will give us m pi r0 raised to 4 by 2. This we have found out the moment of inertia of the bigger disk with the assumption that the central part is not removed.
Okay.
Now we'll try to find out the moment of inertia of only the removed part. So here let's go ahead and find the moment of inertia of the removed part. This will we label that as I2. So let's find out I2. I2 will be equal to the mass of the central removed part, which will be m into pi r square. Very simple. The mass is m is the mass per unit area, pi r square the area of the removed part. So m into r square by 2. So this will be the moment of inertia of the removed part, but this moment of inertia will be for an axis which passes through the center of mass of the removed part.
Right. But हमें R0 जो डिस्क है R0 रेडियस का उसके एक्सिस से निकालना है, right?
Right. So here's the catch. Here we'll use our parallel axis theorem.
Oh, right.
So what the parallel axis theorem told us was that this moment of inertia can be converted for an axis passing through some another axis which is parallel to the center of mass axis. So for that we'll add the quantity, the mass of the part, which is m into pi r square, into the formula said m d square. So here the d will be given by a, which is the distance between the two axes.
Right.
So we'll multiply this by a square. This entire thing will give us the moment of inertia of the removed part about the axis passing through the center of mass of the bigger disk.
Okay. So we'll take out all the moment of inertias with respect to one axis only.
Right.
To avoid confusion.
Right. Because the question also asks us to find the moment of inertia for the axis passing through the center of mass of the bigger disk.
Okay.
Okay. So right now we'll write this down in a concise form, which will give us m into pi r square into r square by 2 plus a square. So here we have found out the moment of inertia of the bigger disk and the smaller disk. As we discussed earlier, we'll now subtract these two quantities to find the moment of inertia about the axis passing through the center of mass of the bigger disk. So this will be given to us by I1 minus I2. A very simple concept. So let's put in the values from our calculated values. This will be equal to m pi r naught raised to 4 by 2 minus m pi r square into r square by 2 plus a square. Now what we are left with is a very simple linear equation which we need to find out, and our answer is ready. So here we'll write it down as m pi. Let's take m pi by 2 out as something common and write it down as r naught raised to 4 minus r square into r square plus 2a square. Here you can see that I've taken the 2 over here outside, so that's why I got the 2 over here on the inner side. This will give us the final answer for the moment of inertia of that body through an axis passing through its center of mass. A very simple question, a very basic question.
So this was a fairly easy question, but we learned the important concept of
the parallel
axis theorem.
Right.
We applied it in this question, and we saw that we need to be careful about which axis we're talking about.
Right.
So that was question number 1.
And one more thing which we need to remember is that the moment of inertia is a scalar quantity which we can easily add and subtract.
Right. Question number 1. Moving on to question number 2. 4 small spheres, each of radius r and mass m, are placed with their centers at the corner of a square of side L. The moment of inertia of the system about a diagonal of the square is. Let's see the solution to this question.
Now here, as we can see in the sketch, the square has been drawn, the 4 spheres have been drawn. Now we'll try to find out the moment of inertia of this entire body. Here again we'll use the parallel axis theorem, but here we can see we have 4 different bodies, and once again we'll concentrate on the concept that moment of inertia is a scalar quantity. So here what we need to find is the distance of this center sphere from the axis, from the axis basically. And we know the moment of inertia, the standard moment of inertia of the spheres. So what we'll do is we can see that the moment of inertia of these 2 spheres will be added without any changes, as both of the axes are the standard axis.
Right.
Here, and then the 2 remaining spheres, which is the sphere on, let's name them A, B, C and D. So we see that spheres B and D will also, we can easily assume 2 axes which are parallel to the axis around which we are supposed to find the moment of inertia, and then we can easily move them with the help of parallel axis theorem.
Right.
So here first basically what we need to know is this distance, because parallel axis theorem needs the distance to be known.
Right.
Here we know that the side of the square is L, and so we can easily guess that this distance which we need, the distance D, will be the length of the diagonal divided by 2. Diagonal by 2. And for a square, we know that the length of the diagonal D is equal to L into root 2.
Right.
Right. So from here we get the distance small d to be equal to D by 2, which will be equal to L root 2 by 2, which we can write down as L by root 2. So this, now we know the distance D. So now the problem has become fairly simple. We just add the moment of inertia of the spheres A and C. Let's write it down as IA plus IC plus, now we'll have to add the moment of inertia of B and D about these axes which we mentioned earlier, plus the parallel axis theorem, parallel axis part of the theorem,
MD square
basically. So here we'll write IB, which will be plus ID, let's write it down as this way, and find out each of them separately.
Okay.
Now IA will be obviously equal to IC, which will be equal to 2 by 5 into m into r square. Very simple. Ia will be equal to Ic into 2 by 5 mr square, because it's the standard axis which we need. Next, let's move on to finding IB and ID, which are a little bit tricky. So the IB will be equal to the moment of inertia about the axis which we have drawn, which will be equal to 2 by 5 into m r square plus the parallel axis part, which will be m d square. D we have found out to be L by root 2. So let's write it down as L by root 2 square. Now this will also be equal to the moment of inertia of the sphere D about the required axis, because we can see that the distance D is same, and also the moment of inertia of the sphere D about the new axis is 2 by 5 mr square only.
Right.
So we can write down as ID is also equal to IB. Now we know IA, we know IC, we know ID, and we know IB. So we know all the 4 required values. All we need to do is just add them up.
Right.
So let's add them up. So we'll have 2 by 5 into mr square, this into 2 for IA and IC, plus 2 by 5 mr square plus m into L by root 2 square, this entire thing into 2 for ID and IB.
Right.
Fairly simple.
So we can easily simplify this expression to obtain the moment of inertia of the system about the diagonal of the square.
Right.
Right.
Here I would like to point out one more concept. This can be very easily simplified, so let's not simplify it further over here.
Yeah.
I want to concentrate on another concept over here. Let me introduce to you to the perpendicular axis theorem. Now, for example, if you have a body which is something like this, we can say something random, something like a flower, we can say.
Yeah.
Okay.
But it can be used only for
2D bodies. So
yeah.
suppose this is a plate of this shape, and if I ask you to find out the moment of inertia of this random plate about this axis, when I have given you the moment of inertia of this plate about an axis passing through its center of mass and perpendicular to its plane.
Okay.
So here what you'll do is you'll use the perpendicular as well as the parallel axis theorem.
Right.
Here you'll basically find the moment of inertia about this axis which is passing through its center of mass. Here. Okay. So this can be easily found out with the perpendicular axis theorem. We learned that Iz equal to Ix plus Iy. Here, as you can see, if you assume this to be the x direction and this to be
but everything is symmetrical.
Y
so
direction.
Ix can be taken to be equal to Iy.
Exactly. So here, as you said, Ix equal to Iy. Therefore, we'll know that Ix will be equal to Iz divided by 2. Iz is given to us, and we can find out Ix. Or basically here we need Iy, since our axis is parallel to Iy. So this will also be equal to Iy. So Ix equal to Iy equal to Iz by 2.
Right.
Now we can easily use the parallel axis theorem and find it out about this axis. So here we see how we can use the parallel and perpendicular axis theorem to our benefit to find out the moment of inertia of any body about any axis.
Right. So in this question we saw the application of parallel axis theorem, and later on we also saw how to apply the perpendicular axis theorem as well. So this is again a fairly easy question. We'll move on to more complicated questions later on. That was question number 2. Now let's move on to question number 3. A T-shaped object with dimensions shown in the figure is lying on a smooth horizontal floor. A force is applied at the point P parallel to AB such that the object has only translational motion without rotation. Find the location of P with respect to C. Let's see how we solve this question.
Here, as we can see in the question, we don't need the body to rotate. So basically, we need to make the rotational force 0, which is the torque. Here, to make the torque 0, we'll see. Let's see how to do it. Now we know that torque is equal to R cross F. So basically, torque is the force applied on the body into the distance about an axis through which it can rotate. Let's assume the center of mass to be this axis. Now, to make the torque 0, the only way which we can do is to make the force 0, which is not the case here. And the other way to make it 0 is to make the R part 0. So here we see that if we make the force pass through the center of mass of this system, we can make the torque 0. Right? So let's find the center of mass of this system with respect to point C as asked in the question. Now, for finding the center of mass, what we can do is we can assume the part AB to be concentrated at point D. We can easily see that the center of mass will lie on the line CD somewhere. Right? So we can let us assume that the entire mass of the part AB is concentrated at point D.
Okay.
Right? So now we are not given anything with respect to the mass of the body. So let's assume lambda to be the mass per unit length for this rod. So we find the mass of AB to be equal to lambda, mass of AB equal to lambda into L, and mass of CD part to be equal to lambda into 2L. Now the center of mass with respect to point C will easily be the mass of AB, which is lambda L, into the distance, which is 2L, plus the mass of part CD, which is lambda into 2L, into the distance of center of mass of part CD from point C, which will be L. The center of mass will obviously be at the center of the rod. Right? So into L.
So here we are trying to find the center of mass of the system.
Right.
And okay.
Right?
Okay.
So this will be divided by the total mass of the system, which will be equal to lambda into L plus lambda into 2L. So we can solve this to find that the value of this entire thing will come out to be 4L by 3. Here we can see that we have found out this center of mass with respect to point C. So we have found 4L by 3, which will be a point P, which is the center of mass of this entire system. And if we apply the force F on the center of mass of the system, there will be no torque produced about the center of mass, and so there will be no rotation.
Okay. Is that okay? That is because in the formula tau is equals to R cross F, R is taken as the distance from the center of mass.
Right.
So R becomes 0, so the torque
Right.
becomes 0.
Right.
Okay, so in this question we saw the application of the concept that when torque is 0, there is no rotation.
Yeah.
This is an important point, and we also saw that when we apply a force at the center of mass,
Right.
when the forces pass through the center of mass, there will be no
Right.
rotation because torque will be 0.
Right.
Right. So we simply found out the center of mass, because if the force F is applied at the center of mass,
Right.
there will be no
So here we have seen that how translational motion is almost equivalent to rotational motion. It's not a very complicated thing which we need to remember. Rotational motion is easy.
Right. Okay. That was question number 3. Moving on to question number 4. A uniform thin rod of mass m and length L is hinged by a frictionless pivot at its end O, as shown in the figure. A bullet of mass m moving horizontally with a velocity v strikes the free end of the rod and gets embedded in it. The angular velocity of the system about the collision is A. mv by L into m plus m, B. 2mv upon L into m plus 2m, C. 3mv upon L into m plus 3m, or D. mv upon Lm. Let's see the solution to this question.
So here we have a rod of mass m and a bullet of mass small m, which comes and hits the rod. We have been told nothing about the type of collision over here. So we need to realize that we can't use any kind of energy conservation over here, as there can be any loss of energy anywhere. So we go ahead and use the concept of angular momentum. We know that the angular momentum of the entire system about point O will be conserved, as there is no external torque, as we had learnt earlier. dl by dt is equal to torque. Since torque is 0, dl by dt is 0, and hence the angular momentum is conserved. So let's conserve the angular momentum of this entire system about point O to find the omega. So the initial angular momentum will be only due to the bullet which is moving towards the rod, which will be easily given to us by m into v into L. here we see that v is the velocity of the bullet, initial velocity. L is the distance of the bullet from the axis. As we had known that the angular momentum of the any particle about any point is mvl. Here we know the initial angular momentum is mvl. Now this we can equate to the final angular momentum when the bullet gets embedded into the rod. So here we'll find that the moment of inertia of the rod about the hinged point O is given by ml square by 3, which we had found out during the introduction, into, let's assume that the system will start to rotate with an angular velocity of omega. This plus we'll have to add the angular momentum of this bullet which is getting embedded into the rod also. So this will be given to us by m into L square, which will be the moment of inertia of just this bullet about the point O about which we are conserving the angular momentum. This into omega. A very simple linear equation which we can be easily solve to find out omega, which will be equal to 3mv by L into 3m plus m. Here you see that the concept is very simple. You might be wondering, why did I choose this problem to be taught? Here the basic concept which we had to concentrate on was that the energy cannot be conserved since we don't know anything about the collision.
The type of collision.
Right. And just in case if the question asks us to find out the energy loss in this entire process, it will be very simple. We'll find out the final energy and the initial energy and subtract them. The initial energy will basically be only the translational kinetic energy of the bullet which is coming in, which will be equal to half into m into v square. The final kinetic energy will be equal to this is the initial kinetic energy. From this we'll subtract the final kinetic energy, so which will be given to us by half into I into omega square, where I is the moment of inertia of the entire system about the hinged point. We already know omega since we have found that out. I will basically be the moment of inertia of both the bodies combined, the rod as well as the mass of the bullet about the point O. So this will be simply ml square by 3, which is the moment of inertia of the rod about point O, plus the moment of inertia of the bullet about point O, which will be ml square. Very simple concept. We know the moment of inertia now, we know the omega, we know all the values, we can find the energy loss in this entire process. So here we have seen how we can relate energy, momentum, conserve momentum, and see how when there is no torque on the body, we use the angular momentum conservation.
Okay, so in this question we saw the application of the law of conservation of angular momentum. We need to check for the condition that the torque, external torque, should be 0.
Right.
And that was question number 4.